Hi everyone, my name is Abhishek. I'm a research engineer at IBM Research, and this work was done as part of my master's thesis at University of North Carolina, Charlotte, under supervision of Dr. Vladek Zitronsky. So let's begin. Question answering. Question answering is an active field of research in natural language processing. A QA system can be classified as a closed domain or an open domain system. A closed domain question system are domain specific and can benefit greatly from domain specific knowledge repositories. Bioasq can be classified as a closed domain QA task. Open domain question answering system, on the other hand, can answer questions from various domains and can exploit different sources on the internet to find answer. The IBM's Watson system is an open domain question answering system that won the TV show Jeopardy in 2011. The system worked by pipelining different components like question decomposition, hypothesis generation, hypothesis and evidence scoring, and answer generation. And then these different components work interlockingly with each other. A more recent approach using deep learning is dynamic memory networks. Uh, the system simulates episodic memory like humans using recurrent network, and it can answer questions through basic transitive reasoning. Another system is differential neural computers. These systems have an external memory and then a controller that can then go through the various facts that the system stores these facts in memory and then can do reasoning on top of that. The system was shown to be able to answer questions given a graph of city. Another type of question answering system is dynamic co-attention network. This system has what they call co-attention mechanism. This system combines a representation of question with a document, and then the system feeds this co-attention output into a LSTM or a recurrent neural network, and then it can go over the set of facts multiple times to arise to come to an answer through transitive reasoning. Uh, Finally, biomedical question answering systems are very domain specific question answering systems that will aid researchers in finding answers to questions instead of going through research papers. Some of the different applications in day-to-day life you can see for question answering are smart assistants like Google Assistant or Siri. Chatbots can greatly leverage from question answering system by feeding in the facts that we right now have as FAQs into them, and then they can say replace customer service by being there and being able to answer questions of customers. Then another type of QA system out there is search engines. So when we search anything on Google, we don't really get answers out of it, but what we get is very relevant link that could answer your query or question. Google does answer a few questions nowadays, so there is a QA system there. BIOS organizes challenges on biomedical semantic indexing and semantic question answering. The semantic question answering task is divided into two phases. Phase A, information retrieval, and Phase B, question answering. The Phase A deals with a retrieval of documents from PubMed that are relevant to answering the question, then set of snippets that can answer the question, and then set of concepts and RDF triples. The Phase B of question answering deals with actually answering the question. And so based on type of question, the answer could be a factoid, a list of factoids, or a yes and no. And then for every question, we are also required to return an ideal answer. An ideal answer is just a summary, a short summary of the snippets, or a natural language answer. The competition is conducted in 5 test batches, released in interval of 1 week, and we have 24 hours to submit our response. The evaluation for phase A is done by using mean precision, mean recall, and F measure, as well as ordinate matrices like geometric mean average and mean average precision. The evaluation of phase B is done differently based on the answer type. So for factoid type answers, we use strict accuracy, lenient accuracy, mean reciprocal rank, as well as automatic and manual comparison to golden standard answers. For list type questions, the evaluation is done on using mean precision, recall, and F measure. For summary-based questions or the ideal answers, the evaluation is done either automatically and manually. The automatic evaluation uses Rouge 2 and Rouge SU scores. For manual evaluation, the answers are evaluated by biomedical experts, and then the final scoring is done based on repetition, precision, readability, and then a mean of all scores. For this competition, we only participated in phase B. Last year was our first time participating in Bioasq, and we only concentrated on phase A. This year, we only concentrated on answering phase B. For answering questions, we need to return answers of type factoid, list, or yes and no based on what type of question it is. And for every question, we also need to return an ideal answer. So an ideal answer is a natural language answer that a user or a person might give given the question. For getting the ideal answer, we use extractive summarization to generate answers over the golden standard snippets. So for every question, Bioasq provides us with a set of golden standard snippets that are extracted from PubMed documents. Each snippet is relevant to the question, and our task is to find the answer among these snippets and then create a natural language answer to the question. Our algorithm, as I said, works by extractive summarization. We have a word limit of 200 words. So we first start by doing sentence segmentation and then identifying biomedical entities. We use Stanford Core NLP for snippet segmentation to get sentences, and then we use MetaMap to get the biomedical entities. We use our own custom code written in Java, and we use Java API to connect to MetaMap to get concepts. So MetaMap is also responsible for tokenization, word sense disambiguation, and connecting to YAMLs, getting all the required mapping. So from our side, we just need to give the sentence as input, and the MetaMap will pretty much take care of remaining work for you. MetaMap was a tool built by Dr. Allen at National Library of Medicine to map biomedical text to UMLS thesaurus. UMLS, which is short for Unified Medical Language System, is a comprehensive thesaurus and oncology of biomedical concepts. UMLS includes tools for meta-thesaurus, semantic networks, specialist lexicon, and lexical tools. So we use the UMLS and MetaMap to do most of the biomedical entity identification. Once that is done, and once we have all the biomedical entities for all the sentences, including the question, we also get the semantic type for every entity, and then we use that semantic type to create a set of semantic types. Each sentence has its own set of semantic types. We will talk more on how that is in the next few slides. Next, we start getting an intersection between the question and the sentence by doing an intersection between the semantic set of question and semantic set of every sentence. And then we select a sentence that has maximum intersection with the question. We select that sentence, we add the sentence as a summary, and we do union of the question set with the selected sentence set, and hence we augment the question's semantic set. We repeat above process until we reach either the word limit or we run out of candidate statements. And the final summary is nothing but concatenation of these selected sentences. And each sentence is ordered based on when it was selected. So our algorithm is inspired from lexical chaining. So lexical chains were introduced by Morris and Hurst in 1991 for text summarization. A lexical chain is a sequence of words in writing or in a document that are clubbed together based on a set of rules. A chain of words represents a concept or a semantic meaning of a sentence or a document, and so a lexical chain can be used to do a semantic similarity between set of documents or find similar sentences, and hence can be used in a summarization task. So for example, the first one is an example of a lexical chain. If you look at the second sentence, I like beer. Miller just launched a new Pilsner. Because I'm a beer snob, I'm only going to drink pretentious Belgian meal. So in this, beer, Pilsner, and ale form a lexical chain. Uh, so well, this lexical chain will tell you that the sentence has to do something with, say, beer or Pilsner or ale, or what these words have in common are their type of an alcoholic drink. And so a lexical chain captures a semantic meaning of that sentence. And if you do apply this on a document, it would capture a central concept or gist of a document. And so the way we use lexical chain in ours is by we use the same concept. We create what we call semantic sets, which we'll be talking more in the next slide, which is very loosely related to lexical chains. Lexical chain have also been used in other tasks like word sense disambiguation, because lexical chains provides you with context to a term and then capturing concept represented by that term. A lexical chain can also be used for machine translation, and in our case we are using this as a biomedical summarization. There's also been research that shows the use of lexical chain for biomedical document summarization, in which they use lexical chains to to find a central idea behind a document, and then they use various techniques to rank lexical chains and then use those to find a final summary of the document. Our algorithm uses semantic set to do sentence similarity. So what is a semantic set? So we first do sentence segmentation and we pass every sentence through meta map. The meta map will identify any biomedical entities that are contained in the sentence. And for every biomedical entity, it will also return a semantic type. We form a set of all these semantic types and we call it a semantic set. So for example, for this question, which antibody is implicated in Bickerstaff's brainstem encephalitis? It identifies two biomedical entities, the antibody and the Bickerstaff's brainstem encephalitis. Uh, so for antibody, it returns two semantic types, AAPP, which refers to amino acid, peptide, and protein, and then IMFT, immunologic factor. And for the Bickerstaff brainstem encephalitis, it returns DSYN, which refers to disease or syndrome. And so the final semantic set of this sentence would be AAPP, IMFT, and DSYN. We also make sure not to have duplicate semantic types. So if, for example, the sentence contained more than two antibodies, you'll get a duplicate because both of them have the same semantic types. In that case, we just keep one of them. In our algorithm, we take input snippets and do sentence segmentation. Once segmentation is done, we pass each sentence through MetaMap to get biomedical entities and build semantic set. Next, we find intersection of every sentence's semantic set with question's semantic set and select the sentence that has maximum intersection or maximum number of common semantic types with the question. That sentence is selected. It is appended to our summary. Next, the question's semantic set is augmented by adding terms from the selected sentence. In other words, we are performing union between the semantic set of question and the semantic set of the selected answer. Uh, Once that is done, the selected sentence is removed from the candidate statements, and we repeat this experiment again until we reach the 200 word limit of summary. The reasoning behind doing this is because Whenever we compare a sentence with the question, we're not only comparing it with the question, but we're also comparing it with other sentences that were selected beforehand, uh, so that they contain information that's not only in the question but also in the previous answer statements that we thought are close to the question. So this slide shows you an overview of our system. So we have input snippets that goes through sentence segmentation, and then we do biomedical entity identification and create set S for each sentence. Then we create set C for the question, and then we repeat this area. We select sentence with maximum intersection with question. Then we do the set C augmentation by doing union with the selected set S of the sentence. We concatenate the selected sentence. We check whether we reach word limit. If we did not, we keep repeating that. When we reach the word limit, we return the set of concatenated sentences as answer. So this is an example of an answer type from our system. So the question is which syndrome is associated with OATP1B1 and OATP1B3 deficiency? And here's the answer that is returned by our system. The summary or the answer is stop when we reach 200 word limit. So the answers usually generated are pretty big. Um, as you can see, the highlighted portion is the answer to the question. And as you can see, our system is able to return the answer in the very first statement. We also did another experiment where we submitted our system with only the first selected sentence as answer instead of waiting for the 200 word plus summary. This slide shows another example. Which protein is found to be mutated in Friedreich's ataxia? And as you can see, the very first sentence is the answer to this question, and our system returns this entire piece as the answer to the question. This slide shows the result of our systems on test batch 5 of task 4B of Bioasq. So these results were acquired through Oracle. So the Oracle system lets you test your system on older data sets, and you can only get the Rouge and the Rouge SU scores, the automatic scores. As you can see, our system got the highest Rouge scores. One reason we think that is because we are returning almost answers that are 200 word long or close to that. So because root scores primarily depend on finding an overlap, our system does get a very high overlap, but that does not always imply that the answers are sound. And so we need a manual evaluation to actually judge a system. This slide shows a result on Bioasq 6B Phase B ideal question answering. So as you can see, we have results for test batch 2, 3, and 5. Do not report results for test batch 1 and 4 because we did not submit our system for those test batches because we couldn't submit it on time before the deadline. As you can see, for test batch 3 and 5, we have two different systems. The UNCC system 1 is the system we just went through. UNCC system 2 is is a similar system, except the answer doesn't consist of a 200 word limit. Instead, it just takes into consideration the first selected sentence as answer. So as you can see, for UNCC system 2, our RUSE scores are low compared to UNCC system 1. So this is because we're not considering every sentence. We're not taking the 200 word limit. The answer size is small, and hence we have very small overlap. But as you can see, the manual scores are still consistently high, which tells us that the first selected statement itself does consist of answer. Uh, that concludes my video presentation. Thank you again to Bioasq organizers for letting me send in my video. Thank you.